In this video, we'll discuss the need for cleanroom infrastructures in chip manufacturing. In particular, this video will introduce the concept of manufacturing yield, as well as provide an overview of the nanofabrication cleanroom infrastructures. In the previous video, we learned about the economics behind chip manufacturing. In particular, we discussed the efforts to increase the wafer size over time in order to increase and integrate as many as transistors as possible on a single wafer. Furthermore, we described that chip manufacturing involves replicating multiple copies of a microchip across a wafer. The main reason behind these considerations is to decrease the cost of electronics. However, a main assumption here is that all fabricated components meet the target specifications set out during the design. In practice, however, not all fabricated components on a single wafers would meet the target specifications. The illustration here shows an example of a wafer with multiple copies of a microchip. In this example, several microchip dies are incomplete because they are located at the corner of the wafer. These partial dies are denoted in yellow here. In addition, there are microchip dies that are defective, which are indicated in red color in this illustration. As a result, only a subset of microchip dies will meet the target specifications, which are denoted as good dies in green color here. With this backdrop, the manufacturing yield is defined as the ratio of the number of good dies to the total number of full dies across a wafer. Since not all microchip dies are good, the cost of manufacturing can be retrieved only from the good dies. Therefore, increasing the manufacturing yield is an important factor for lowering the cost of electronics. Before we delve into the sources of killer defects, let us consider how the size of die impacts the yield. In this example, the wafer has 14 full dies. However, as illustration shows, several killer defects coincide with 6 of the full dies on this wafer, thereby rendering them defective. As a result, there remains only 8 good dies on this wafer, which are marked with green color. With this information, we calculate the yield of this wafer to be 8/14, which is equal to 57%. Now let us consider another design where the microchip die is smaller than the previous design. As a result of this design change, we end up with 40 full dies on the same wafer size. In this example, we keep the characteristics of the killer defects in terms of shape, count, and location identical to the previous example. Similar to the procedure we used earlier, we count 31 good dies, such as these dies, on this wafer. Now, using this information, we find the yield to be 31/40, which is equal to 77.5%. This example illustrates that microchips with larger die size are more vulnerable to the yield loss due to the killer defects. Particles deposited on a wafer during fabrication are the main source of killer defects. Such particles may originate from many sources, including people, machines, chemicals, and human handling. These particles may be airborne or may be suspended in liquid or gases. The illustration on the left-hand side shows a few examples of contamination particles such as sodium, iron, gold, and copper particles, as well as photoresist residues. These particles and contaminations may be generated during wafer handling or prior processing steps. Also, particles generated by human, like hair, can be fatal in chip manufacturing. The image on the right-hand side shows the micrograph of a human hair, which is about 50 micron diameter. The removal or significant reduction of particle sources is essential in chip manufacturing. Particles are always present in distribution of sizes and shapes as illustrated in this plot here. The airborne particles that are of concern in chip manufacturing plants range between about 10 nanometers to about 10 micron in size. In room air, particles smaller than 10 nanometer tend to coagulate with each other and form larger particle sizes. Those particles larger than 10 micron tend to be heavy and precipitate on surfaces. Particles between 10 nanometers to 10 micron can remain suspended in air for long periods of time. Accordingly, these particles can cause significant yield loss in chip manufacturing. Therefore, removal of such small particles from the air is crucial for improving manufacturing yield. This is done through the construction of clean room environments. The factories in which microchips are manufactured clearly must be clean facilities. Clean rooms provide the first level of defense against defects that affect yield. Clean rooms not only provide reduction in airborne particles, but also they provide tight control over temperature and humidity. Furthermore, different sections of a clean room may have different cleanliness ratings in terms of particle density depending on the needs of the fabrication process. This brings us to the question of how to quantify cleanliness. The cleanliness of the air in chip manufacturing plants is described by International Standard Organization or ISO standards. The table here shows the different ISO classifications from ISO 1 to ISO 9. For example, a typical office building is classified as ISO 8 or class 100,000. Note that prior to adoption of ISO standards, the classification was done by indicating the class of a clean room. The class in this context had a simple meaning. Class X simply meant that in each cubic foot of air in the factory, there was less than X number of particles greater than 0.5 micron in size. For example, class 100 means that there are less than 100 particles with 0.5 micron in size per cubic foot, or equivalent of 3520 particles per cubic meter. This class of 100 clean room is the most typical clean room in academic environments. In contrast, the air in an advanced chip manufacturing plant is ISO 1 in most critical areas. The cleanliness is achieved through a combination of air filtration, air circulation, clean room design, as well as careful elimination of particle sources. Since the sources of particle can never be eliminated, constant air filtration is used to remove particles as they are generated. This is achieved by recirculating the air through high efficiency particulate air or HEPA filters. The recirculated air is forced through these HEPA filters before it enters the clean room again. The HEPA filters are about 99.97% efficient at removing the particles from the air. Note that the makeup air here replaces the air lost due to exhaust or during the air circulation. Lastly, in modern cleanroom environments, the process tools as well as pumps, vacuum pumps for example, are placed outside the cleanroom areas to minimize particles due to these machines. As I noted earlier, people can generate particles due to exposure of their hair, skin, and clothing. In fact, a person in an idle mode, for example, sitting on a chair, typically emits in the range of 5 to 10 million particles per minute. This number would increase to about 100 million particles per minute when a person is running. These particles numbers are huge. Therefore, a crucial consideration is to significantly reduce the particles emitted by people. This is accomplished through a full coverage from head to toe by wearing bunny suits, face masks, as well as gloves. In summary, in this video we learned that continuous filtering of particles in a clean room and wearing a proper clean room suit are essential considerations for improving the manufacturing yield of electronic chips.